By the end of this video, you'll understand why the fastest weapon on Earth doesn't belong to a lion, a shark, or a bird of prey. It belongs to a shrimp. Not fast like an arrow. Fast like a bullet fired point blank. And the strike itself isn't even the most disturbing part. The peacock mantis shrimp carries a club-shaped appendage called a dactyl, and when it strikes, that club accelerates at over 10,000 times the force of gravity, reaching speeds close to 23 meters per second, comparable to the muzzle velocity of a .22 caliber bullet. It hits so fast that the water in front of the club can't move out of the way in time. Instead, the pressure drops so low it forms a vapor cavity, a cavitation bubble, that collapses a fraction of a second after the club has already made contact. That collapse alone can crack aquarium glass, and when the bubble implodes, it briefly generates a flash of light and heat that, for a fraction of a millisecond, approaches temperatures near the surface of the sun. But here's what actually matters. The shrimp isn't strong. Its muscles could never generate that kind of speed on their own. What it has is a saddle-shaped structure in its arm that works like a loaded crossbow. Muscles slowly compress it, storing elastic energy over time. Then a latch releases it all at once. The strike happens faster than the shrimp's own nervous system could ever consciously control it. This isn't strength. It's a mechanical spring built by evolution to bypass the speed limit of biological muscle entirely. But that's nothing compared to an animal that can survive being launched directly into the vacuum of space. In 2007, the European Space Agency sent tardigrades into low orbit, exposed them to the vacuum of space and to unfiltered solar and cosmic radiation, and when they were brought back down, a portion of them revived and reproduced normally. Here's the mechanism. When a tardigrade senses extreme dehydration, radiation, or cold, it pulls in its limbs, expels almost all the water from its cells, and enters a state called a ton. It replaces that lost water with a sugar called trehalose and a set of protective proteins. One of them, nicknamed DSUP, physically shields its DNA from radiation damage. Metabolism drops to a level so close to zero, it becomes nearly undetectable. The important part isn't that tardigrades are tough. It's that they're not fighting the damage at all. They're removing the conditions that make damage possible. Death requires an active metabolism to fail. A tardigrade in a ton state simply isn't running one. It doesn't survive the vacuum of space. It exits the game entirely, then re-enters it later, on its own terms. Compare that to an animal that's running 2 separate communication networks at the same time, using 2 different senses. Elephants produce infrasound, calls below 20 hertz, under the range of human hearing, that can travel through open air for several kilometers. Other elephants pick these calls up not just with their ears, but through their feet. Elephant feet contain dense, fatty pads and pressure-sensitive structures called Pacinian corpuscles that pick up vibrations traveling through the ground. Some of these seismic signals arrive faster through solid earth than the matching sound does through air. Researchers have recorded elephants freezing and shifting stance in response to ground vibrations from calls too far away to be heard normally, seemingly cross-referencing what their ears heard against what their feet felt. That's the part worth sitting with. This isn't one sense doing a better job. It's a redundant system. 2 independent channels, air and ground, confirming the same information through completely different physical media, so a single point of failure in either sense doesn't cost the herd the information. But that's nothing compared to an animal that can hang its entire body weight from a pane of glass using no adhesive at all. Gecko toe pads are covered in millions of microscopic hair-like structures called setae, and each of those splits into hundreds of even smaller tips called spatulae. Individually, each one generates an almost immeasurably small attraction to a surface through van der Waals forces, a weak pull between molecules that exists at extremely short distances. Multiply that by billions of contact points, and the combined force is strong enough to support the gecko's full weight upside down. There's no glue, and no suction involved anywhere in this system, which is exactly why geckos can detach instantly, something a sticky adhesive could never do. They don't peel off by force. They change the angle of their toes, which increases the distance between the spatulae and the surface just enough to switch the attraction off. It's not an adhesive. It's a contact angle, acting like a mechanical switch, on when flat, off when peeled. Compare that to an insect that survives detonating a chemical explosion inside its own body, on demand, over and over. The bombardier beetle stores hydroquinones and hydrogen peroxide in two separate chambers. When threatened, it releases both into a reinforced reaction chamber lined with enzymes that trigger a violent exothermic reaction. The mixture reaches close to the boiling point of water and is expelled as a rapid burst, not a steady stream, but discrete pulses, up to several hundred per second, aimed through a rotating tip at the end of its abdomen. What keeps the beetle from cooking itself isn't armor. It's timing. By firing the reaction in rapid, separated pulses instead of one continuous burn, the beetle limits how long any single moment of heat has to build up before the next pulse resets the chamber. This is less a weapon and more a pressure-regulated combustion engine, built entirely out of soft tissue, that survives its own detonation purely through the rhythm of how it fires. But save the biggest one for last. An octopus has roughly 500 million neurons, more than most mammals, but only about a third of them sit in its central brain. The remaining two-thirds are distributed across its 8 arms, with each arm carrying its own dense cluster of neurons capable of processing touch and taste independently. In lab conditions, a severed octopus arm has been observed continuing to react to stimuli and even reach toward food on its own, without any signal from the central brain at all. This isn't a body being controlled by one intelligence sitting at the top. It's closer to 8 semi-independent problem solvers that happen to share a body and occasionally check in with a central coordinator. When an octopus solves a puzzle or navigates a maze, it's not one brain doing the thinking. It's a distributed system, closer to a network than to a single mind, and that might be the closest thing on this planet to what non-human intelligence actually looks like. That's Wild Protocol. Follow the channel. Every biological system on this planet runs on rules stranger than anything in fiction, and we're only getting started. Subscribe to Wild Protocol.